So, I have WL, I have weight of the arm, now when you look at joint reaction forces, it is always a good idea to take the two perpendicular components along the axis and perpendicular to the axis, because you are looking at the dislocating or stabilizing component and the component. So, you can take this as J A axial component and J N normal component. And now, in this position, you know that muscle insertions can change, the the angle changes depending on your posture. Let us say the muscle insertion angle has now changed to, in this particular orientation, is now 25 degrees. Okay. So, the same muscle now it is pulling at an angle of 25 degrees. Earlier it was pulling at 30, now it is pulling at an angle of 25 degrees. And this angle here is 65. Now, do the same analysis and see what you have gained or lost. So, let us just say we are looking at the muscle force. So, let us just say sigma m about the shoulder equal to 0. So, I can write it as F m sin 25 into, if this point is A, this is B, this is C. Oops. S A minus W A into S B sin 65. So, I can just take, I can take this load and take the perpendicular momentum to compute the moment about that joint, minus W L into S C sin 65 equal to 0. So, essentially if you look at it, by moving the load closer, okay, by changing that angle from 90 to 65, I am reducing the external moment by this much from what it was earlier by sin 65. Okay. So, I am reducing that. So, you would expect that perhaps the muscle force would decrease. Okay. Compute it and see what happens. And you end up getting 0.16, are you sure? So, I got something else.
0.375.
You get 0.375 W. So, whatever advantage you gained by moving the load closer, by reducing the moment arm of the load, you actually lost because the muscle insertion angle changed. Sin 30 was in the denominator earlier. Now, sin 25 is in the denominator, and that actually slightly increased the load on the muscle. Right? In reality though, this is a simplified analysis. I am assuming only one muscle is acting. I have not looked at any of the antagonists for this particular exercise, right. So, it is possible that, so if I look at say the muscles like the latissimus dorsi, if that is in an antagonist position when I have stretched it out, right. So, that may actually be exerting a greater force when I am holding it up like this than when it is not stretched as much. The passive tension in it would be lower when it is not stretched as far. Okay. So, this analysis with a single muscle does not tell me the whole story. Okay. It just tells me that this agonist muscle now actually has to exert a greater force because its angle of insertion has changed. Its angle of insertion is more disadvantageous now, but unless you do a more complete analysis of what are the muscles acting against this particular action. This is the muscle causing this or holding it in this position, but there are muscles that are also so that is where you have to go to more sophisticated analysis like the optimization, for instance, where you have multiple muscles and then you decide okay, these are probably going to be acting. So, this is, so you have to remember that this is an analysis that gives you some insight, but does not give you the true picture completely, because it is a model and it is a simplified model, it is a fairly simplified model. So, this is the case. Now, look at the third situation where, so here it has actually muscle force is actually increased slightly because of the disadvantages. So, whatever advantage you gain by reducing the moment arm about the shoulder of the external loads, you lost because of the disadvantageous angle of insertion of this muscle. Now, the third situation, you realize that okay, it is too low, the traffic is not going to be able to see it early enough to stop. You now bend your arm at the elbow and hold it up like this, hold up the sign like this. So, let us draw the free body diagram for that case. So, I have the weight of the load, the weight of the arm, the lower arm. So, not the full weight, just the weight of the lower arm is now acting here, right. If I bend my, earlier I had the full weight of the arm acting at this point. Now, the weight of the lower arm will be acting here and the weight of the upper arm will be acting somewhere between in this. So, let us say this is now the weight of the upper arm, and then I have my muscle force again acting at 30 degrees. Now that my shoulder has come back to this 90-degree abduction, I have, and then I have Jx sorry. And now I have to tell you that okay, initially weight of the upper arm is 0.03 W, weight of the lower arm is 0.02 W. Remember, I had given you the weight of the whole arm as 0.05. If you look at the structure, the upper arm is generally heavier than the lower arm. Yes.
Isn't the weight of the lower arm balanced by the joint force at the elbow? So
It's acting at that point, right?
yes.
It's an external force. It's an external force that's acting, that's going to have an influence on the force at the shoulder.
Why not consider the joint forces at the elbow?
Because this is not, why not consider?
Joint forces at the elbow.
Yeah, you could do that, then you would have an equal and opposite, you would have it in the, if you just consider the free body from shoulder to elbow, you would still find the effect of this external force as a joint force. Okay. So, now I do not because the joint forces are internal, I do not put them in addition to this, I am only applying the external forces. Okay. And now let me compute the, so let me say this weight of the weight of the, sorry, the length of the upper arm and lower arm are equal, right. So, we had here what was the, this was 0.4, this is 0.2. So, the weight of the upper arm acts at 0.1. This is 0.1 h, and these two, their moment arm is 0.2 h. Now calculate the muscle force. Again, sigma f x equal, if you just want to calculate the muscle force, you can just use the moment equation, because that will eliminate two unknowns j x and j y. So, using the muscle equation, I get f m sin 30 into S A. So, what do you get? Minus of W L plus W lower arm into 0.2 h equal to 0. Oh, sorry, thank you. Minus upper arm into 0.1 h equal to 0, 0.225. So, you get F m equal to 0.225 times the weight. So, now you see a significant decrease in the muscle force that needs to support this external load. So, this is about a 36% decrease from case 1, the first case where the arm was fully extended at the elbow. Okay. So, again here if you look at the muscle force, the x component is your stabilizing component or dislocating component depending on the angle. Okay. Is it trying to pull the pull the arm out of the socket, the shoulder socket, or is it trying to press it in to that. Okay. And in the case of the shoulder, your socket is actually quite shallow and the ball is, you know, you have this ball and socket joint, but the socket is fairly shallow, which is why you have a wide range of motion at the shoulder. The range of motion at the shoulder joint is the highest among the joints in the human body. Even the hip is more stable. You don't get the same range of motion. You can't do this with your legs, right? You can do a lot of the range of motion at the shoulder is much higher than at the hip joint. These are the two ball and socket joints that you have, and you find that at the shoulder. So, because if you look at humans, we use the arms and our hands for a lot more activities that require that dexterity, that range of motion, right. And the loadings on the arms are lower, relatively lower than the loadings on your hip and your lower limbs, because the entire body weight is being supported by the lower part of your body. So, the arms are actually free to do more things, and so you have, the body is designed so that you have a larger range of motion. You have way more degrees of freedom. If you count the number of degrees of freedom starting from your shoulder to the tips of your fingers, so many things you can do, so many degrees of freedom. If you look at a person playing a piano, the number of degrees of freedom they are coordinating to accomplish that task, it is mind boggling, really. So, that is but because the shoulder is also shallow, and it is also more susceptible to injuries. So, if it is easier to dislocate, dislocating your shoulder is much easier than dislocating your hip. So, if you carry too much load in a position where it is likely to, or if someone applies a force, when the muscle force is actually contributing to the dislocation, then the chances of shoulder injuries become higher. Okay. So, what you gain in motion, you lose in stability. So, it is not a very stable joint. So, just just look at the range of motion. If you see the range of motion at the shoulder joint, you have 230 degrees of flexion extension, you have 170 degrees in abduction, adduction, and another 170 degrees of inward and outward rotation. Okay.
What prevents my arm from going back like this?
The other ligamentous structures and the muscles, the capsule, the connective tissue around it. Right? So, if you had a skeleton without all that, you just had the joint, you will probably be able to make it go the full round. Okay. Any questions? So, that is basically by when you can produce more motion. So, in your case itself, if you do not perform a certain type of activity, you feel stiff, and then slowly if you practice that, you start stretching the soft tissue and the muscle and all that, right. So, in the case of where they train for flexibility, right, they work on their muscles and their soft tissues to achieve that flexibility. So, in some people, you have their joints are such, they may be like this double jointed, you may have seen, they can actually move their arms in ways that most of us cannot move. So, there may be some difference in their structure which enables them to do it. See, it is essentially two bones meeting at a joint, and then you have all these things that are surrounding that joint. So, how the and it is all living tissue in some sense, right. It is all the muscles, bones, ligaments, everything is living tissue that you are talking about. So, in the human body, essentially it is use it or lose it. So, if you do not use a muscle, so if you have a fracture for instance, why do you need to go into therapy? If you have not used a certain set of muscles, the muscles actually start shrinking. It is called atrophy. They start shrinking, and then you have to go through an exercise program to actually start building the strength up. So, if you are if you have some health problem and you are bedridden for some time, you can't suddenly just get up and walk because your muscles have become weak. So, you need to build up the strength. It is the same thing with flexibility, everything, it comes from doing doing something repeatedly. If you do yoga, the first time you are not going to get the same range of motion that you get at a particular joint, right. But if you keep practicing it, if you keep stretching, every time you stretch a little bit more, the soft tissues will allow that, and that is how you gain flexibility. Okay. So, it is possible, but most of us in normal activities of daily living do not really push. Our muscles are usually operating at the very low end of their capabilities. We are not pushing our muscles to the extremes that they are capable of. You see, the ones that are pushing them are like the athletes, the weightlifters. When you look at there, most of them are started out like us, right. Everybody starts out as children, becomes adults, and but you can change the structure of some of these by your diet, by the appropriate exercise, etc. So, concentric actions, eccentric actions, different. So, when you look at strength training itself is a very fascinating area. and a lot of people do research on how best to build up the muscles so that they can exert the kind of forces you need to do. You can't do it if you just go and start lifting a load, you are going to injure yourself pretty badly, but it is something that you can build up to. So, that is why it is a gradual building up that happens. A person does not become a weightlifter in a day. It's the muscles have to be trained to do that. A gymnast does not become a gymnast in a day. A ballet dancer does not become one in a day. You know, the ballet dancer supports their entire weight on the toe. Okay? Most of us will not be able to do that. It comes from, and if you see their foot, it's it's plantar flexed so much. Okay, that's something that most of us would not be able to achieve that kind of range of motion. So, when we talk about this range of motion, we are talking about in normal, without really doing anything special. What is the range of motion that you can? This also changes with age. As you get older, your muscles, your composition, your body composition changes. Muscle compositions change. So, if you look at a scan of a muscle of a 50-year-old versus the muscle of a 20-year-old, you will see there are differences in that. That is the normal process, that is the normal process of aging and growth. So, you grow up to a certain point, then your body starts decaying, whether you like it or not. You can maintain it at a certain level because of what you do, which is why exercise and all that is important. But in the case of the body, it is very true that if you do not use something, you lose it. The body just assumes you do not need it and says, okay, let me divert it to something else. Okay. So, it is very important. So, when physical activity is important for that reason, because and it is important even when you are young, good diet, physical activity, all these are important even when you are young, because that is going to determine how fast your decay is. Okay. And also of course, the habits that you develop will stay with you. So, it is very important that you take good care of what you have been given, so that you can put it to use and so that it will serve you well for your lifetime. Okay? All right.